Okay, so picking back up with the previous example, we're going to actually practice, oops, see I forgot the key thing there. Don't forget to square it. We're going to actually practice integrating this by hand. Doing it on the calculator, as long as you're in radian mode and polar mode, is pretty straightforward, and it will feel very familiar to what we did with other area problems. But doing it by hand, you're going to actually need to trick up your slave for it. So let's give this one a shot. So the first thing I do when there's something being squared that's pretty gross is I'm just going to expand it. Okay, so I'm going to leave the 1/2 out front, and I'm just going to do 2 plus 2 sine theta times itself. So that would give me 4 plus 2 sine theta times 2 plus 2 sine theta times 2. So that's 4 sine thetas. And then we would square this guy for it, multiplying it by itself, so 4 sine squared theta. Okay, and since I'm seeing a lot of even numbers here and a 1/2, you can think of it however you like. Either you can factor a 2 out and cancel, or just distribute the 1/2 through. Either way, this would become 2 plus 4 sine theta plus 2 sine squared theta, d theta. Now, with what we have in our toolkit for integration, the first two pieces are not very scary. However, integrating something like sine squared theta is not something you really have in your toolkit right now. We might be tempted to attempt integration by parts, but if you remember, having a trig function with integration by parts isn't helpful if both are trig, right? Because neither of them would ever actually approach 0 no matter how many times we derived. So that's just going to leave our wheels spinning. And substitution doesn't help when it's the same function twice and its derivative doesn't show up anywhere. So sine theta times sine theta, thinking of it that way, isn't actually going to help us. So you're actually going to use an identity to rewrite it completely before deriving it. And I'm sure at one point you may have known this in pre-calculus, but it's been a while. And these are called the power reducing formulas. And you are going to want to become best friends with them because they save you in these situations when you don't have a calculator and you have to integrate this stuff. So there's 2 of them we'll use a lot. I'm just going to make like a little bubble here so we remember what both of them are. And they come from things to do with the Pythagorean identity combined with double angle formulas. So in this case, sine squared theta is equal to 1/2 times 1 minus cosine of 2 theta. Okay, and a lot of times you'll see that actually multiplied out as 1/2 minus 1/2 cosine 2 theta. That's how I write it a lot of times. And then cosine squared theta is almost the same thing. It's 1/2 times 1 plus sine, miswrite, plus cosine 2 theta, which again, often you'll see it actually distributed through as 1/2 plus 1/2 cosine 2 theta. So they're very similar. Sine simply has a subtraction, whereas cosine has an addition. Okay, but this really makes your life so much nicer if you just can hang on to it in your memory somewhere, or learn how to derive it from your identities. That's up to you. So we're going to actually rewrite it now using that. So it would become A equals 0 to 2 pi 2 plus 4 sine theta. We had no problems with those. Those were great. But now instead of plus 2 sine squared theta, I'm going to have plus 2 times 1/2 minus 1/2 cosine 2 theta. And I can actually take it from here, right? And we can actually distribute that 2 to both of the halves, which is quite nice in this particular situation. That won't always be so pretty. We're so close to being ready to actually derive. So that's just going to be plus 1 minus cosine 2 theta d theta. I'm going to go ahead and combine the 1 and the 2. And now we are finally ready. Oh, see, and then I messed it up. Wait, oh my gosh. Oof. We are finally ready to integrate. So 3 will simply become 3 theta. Remember, it's with respect to theta. 4 sine theta, well, sine is the derivative of cosine, but actually it's usually negative, so we're going to have to kind of compensate for that, and it's really going to become plus a negative 4 cosine theta. And then cosine of 2 theta, again, I'm really using substitution here. I know if I did the chain rule, I'd get an extra 2, so we're going to need an extra 1/2. And sine of 2 theta. And all of this is being evaluated between 0 and 2 pi. Okay, so now let's actually think about this. So let's plug in our 2 pi. So, well, 3 times 2 pi is simply 6 pi. Cosine of 2 pi is just going to be, the x value at 0 is 1. So that's just going to be a minus 4 times 1, which is minus 4. And then sine at 0 is simply 0. So, or sorry, 2 pi, excuse me, because you know that it's very different. Sine of 4 pi is essentially the same as sine of 2 pi, which is essentially the same as sine of 0, all of which are 0. So that's going to be a minus 0. Now we're going to plug in 0, so 3 times 0 is 0. Cosine of 0 is 1, so again a minus 4. And then, as we just talked about, this is simply going to be 0. So when we simplify this, we get 6 pi minus 4, and then minus a negative 4 is really plus a 4. So our grand answer is an area of 6 pi.